Okay, a couple of announcements before we start talking about digital circuits. Well, continue to talk about digital circuits. Homework 2 is due tonight. Please submit that on Gradescope. Homework 3 will be posted later today. That will be due the next Friday. Studio 2 is due the coming Wednesday. So that's September 23rd at 11:59 p.m. And when you submit, don't forget to add your partner to the submission. One submission per group. So one person in the team can volunteer to submit, and when they do that, just after they submit, it'll give you an option to add a partner, and you should add your partner to for them to also be attached to that submission, and for them to also get the grade that you get. Now, the partners, it's their responsibility to check whether they were added to the submission or not. So make sure that you and your partner coordinate the submission. Studio 3, which is going to be probably the most interesting studio, will be posted later today. And I have a video that I'm going to make available to you guys. It's going to be called Studio 3 Information. So I would recommend you guys to watch that video, then get started. So the video talks about how we are going to design multiple modules and then connect them together in order to make a bigger design. Others, am I breaking up? Okay. So, John, it might just be you. All right. So, I want to emphasize on the importance of Studio 3, not just because it is the most interesting studio, but Studio 4 and 5 will rely on the things that you learn in Studio 3. So, in other words, Studio 4 and 5 will go much faster and easier for you if you learn the things that we are trying to convey in Studio 3. I will post that later today, but it will be due. Oh, good question. So it'll be due after 2 weeks. So Studio 3.1 and no. So there is just Studio 3, right? So it'll be due, let me check, 2 Wednesdays. So 23rd, 3rd. So we are talking about October 7th is when it is going to be due. And the only reason why such a 2-week time period is being associated with this is mainly because it is a different studio, right? It goes away from behavioral modeling and we start talking about structural modeling. Okay, quiz 5 is available on Gradescope for you to answer anytime today, but it has to be today. Okay. Any questions or concerns before we get into lecture 2.2? How many total studios? We might get to maybe 8 to 10. Not all the studios are going to be based on the FPGA board. Some of the later ones will be simulations using LogicWorks. Okay, let's get started. So we were talking about how to implement logic gates using transistors, and the way we were looking for transistors is NMOS and PMOS transistors, right? So we were trying to build a pull down network and a pull up network, and they were complementary to each other. We discussed that. So in this case, we are trying to build a NAND gate, which is essentially a NOT of AND gate. And we have 3 NMOS transistors over here that are in series. That's my pull down network. 3 NMOS transistors in series. And I want you to start noticing a pattern of NAND gates having the pull down network or NMOS transistors in series. And the moment you come up with the pull down network, pull up network becomes quite simple because it's just going to be the complementary of the pull down network. So the pull up network in this case has 3 PMOS transistors in parallel. And the output Z is connected between the pull down and the pull up network. So the drain terminal of Q1 and the drain terminal of Q2, Q4, and Q6, they're all connected to Z. That's the output. A, B, C are my 3 input binary variables. Those are essentially connected to the gate terminal of all the transistors, right? So Q1 and Q2 are being controlled by the gate voltage at A, Q3 and Q4 are being controlled by the gate voltage at B, and so on. So the claim over here is this is actually a 3-input NAND gate. So let's take a look at, let's answer some questions, right? So for example, when is Z going to be 1? Let's answer that question. When is Z going to be high or logic 1? Well, the only time Z can be, well, let's do a simpler question. How about low? When is Z going to be low? So I'm trying to look at a case where Z is connected directly to ground, right? So Ajit is absolutely right. A, B, C are all high. So the only time when Z can be 0 is because these 3 transistors, Q1, Q3, Q5 are all in series, each of them have to be turned on, right? So Q1 has to be on, Q3 has to be on, Q5 has to be on. And for that to happen, A has to be high, B has to be high, C has to be high. All 3 of them being high, that's the only time Z will be low. So that's our last entry in the table. And for every other entry, at least one of them, A or B or C, is going to be 0 or low, which means Z will not be able to go to ground. Z will not be low. At those times, Z will actually be connected to VDD, a high voltage, through one of these paths, at least one of these paths, Q through Q2, through Q4, Q through Q6. So those are all the first 7 entries in the table. So all those are right here, all the 7 entries. And for that, Z is always high. Now, if we zoom in on this and try to take a look at Z and how it relates to the inputs A, B, and C, we can see that it is exactly the opposite of AND functionality. In other words, I can say Z actually equals A and B and C, but it is exactly the opposite of that. So I'm going to put a bar over it. So that's my NAND gate for which the symbol is drawn right here. So how do I make a 3-input NAND gate? Put the NMOS transistors in series, that's your pull down network. Put the PMOS transistors in parallel, that's your pull up network. That's how you would do a NAND gate. Now, if somebody was interested in designing AND gate, what would they need to do? And this is something that we discussed last time, but I just want to recap that. Now, if I want AND gate, I would need to do NAND followed by a NOT gate. So that will make it double complement, right? So what you get here is A, B, C, NAND, and then because you have a NOT gate, you will have a double complement. So the double complement will cancel out, and what you end up with is simply A and B and C. So that's how you implement a AND gate. Another way of looking at it is AND actually requires 2 more transistors than NAND. and requires 2 more transistors than NAND. So NAND gates are actually cheaper than AND because you are putting a NOT gate in front of it. And in the previous class, we talked about how to do that, right? Like we said, okay, this is my, let me go back here. So that's my a NOT gate. So I would put this in front of, so the Z that we had earlier, that's what I would connect over here. And this will be my AND output. So I would have to cascade the NOT in front of the NAND to get AND. Let's go back and let's see this. Where are we? We are right here. Let's do a quick transistor count. 3-input NAND gate requires 6 transistors. Then you see them, Q1 through Q6. 3 of them are NMOS, 3 of them are PMOS. So when you add the NOT in front of it to get AND functionality, you are actually adding 2 more transistors. So you get a total of 8 transistors to implement a 3-input AND gate, right? So 3-input AND will require 8 transistors. 6 of them to get NAND, 2 of them to get NOT. There's a question on the chat box. Could you make an AND gate by switching VDD and ground, or will that not work? That will not work based on the construction of the NMOS and PMOS transistors. There was a question on Piazza, I believe, that was answered that was related to this. The only way we can use transistors to synthesize AND functionality is the way I have talked about here. Now let's go into the world of NOR and OR, right? Things are exactly going to be appearing in patterns and complements. So for example, now what we have is a pull down network that has 2 NMOS. So the pull down network has become what? Pull down network is 2 NMOS transistors in parallel. And my pull up network, I need this. My pull up network has become what? 2 PMOS transistors in series. Now I want you to notice this being like the other side of the coin, just the opposite. Everything is becoming opposite. Serial is becoming parallel, parallel is getting serial, series. NMOS is becoming PMOS, right? So you see this in the pull down network, you had 3 NMOS transistors in series. Now what you have is 2 or 3, depending on the number of inputs, 2 NMOS transistors in parallel, right? And then the pull up network has 2 PMOS transistors in series. For NAND, we had 3 PMOS transistors in parallel. Could you remind us why you would use parallel instead of series? Now, that is related to the gates themselves, right? So if you want to get AND functionality or NAND functionality, right? How do you get AND, right? All the conditions have to be true. If all the conditions have to be true, they have to be laid out in series. So that's why for NAND functionality, you have your NMOS transistors laid out in series and your PMOS transistors are in parallel because it's a complementary MOS functionality here. Now for NOR, one of the paths should be connected. So you have 2 paths being offered to go to ground, right? So in this case, you can ask the question, when is Z going to be high? When is Z high? Well, the only way Z can read high is when both Q2 and Q4 are on. When are Q2 and Q4 both on? Because they're in series now. When are they both on? The only time Q2 and Q4 are on is if A and B are low, right? So the only time you get this is the first one. When A and B are low, Q2 and Q4 are on, and Z is high. For all the other times, Z will be low, connected to ground, because it has two paths, Q through Q1 or through Q3. And if you observe this table here, we can say that this is exactly the opposite of OR truth table, right? So here you see high, low, low, low. For OR functionality, you would get low, high, 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 right? For that particular sequence of inputs, 0, 0, 0, 1, 1, 0, 1, 1. And that's how you synthesize a NOR gate. You would have to put the pull down network in parallel and the pull up network becomes in series. And you can expand that to 3 gates, right? So what would need to change if I wanted a 3 input NOR gate? If I wanted a 3 input NOR gate, I would add one more transistor in parallel here, maybe Q5, which has to be NMOS. And I would add another PMOS transistor in series here, maybe Q6. And both those transistors that I just added need to be controlled by that new input, maybe C, right? So that would still require 6 transistors in total, just the same way as we had a 3 input NAND gate. The question online, does it matter which input is connected to which transistor? Not really, it doesn't. But if you follow a pattern, then it will be easier for you to analyze the circuit. All right, next, let's see. Now, the next question obviously is, you got NOR, how do I get OR? And we are going to do exactly the same thing that we did earlier. We are going to say OR is equivalent to NOR followed by NOT. Add a NOT, absolutely. So this guy will require certain number of transistors, maybe 4, maybe 6, right? In general, it will be 2n, where n are the number of inputs to the gate. But then you will have to add 2 more transistors because of the NOT in front. And that's how you would synthesize an OR gate. Let's quickly recap what we have dealt with so far. CMOS and OR and buffer are actually related to NAND, NOR, and a NOT gate. So if you want a CMOS AND gate, we would need to connect the output of the CMOS NAND gate to a CMOS NOT. And we made this conclusion before. AND requires 2 more transistors than NAND. And a similar operation for OR, right? So if you want an OR gate, you would say NOR followed by NOT. That's how you would get OR. And a CMOS buffer can be implemented using 2 cascaded NOT gates. So you would put one NOT gate and then you would follow it up with another NOT gate. That's how you would get a buffer. So that essentially requires 4 transistors. One buffer is going to require 4 transistors. Now we come to one of the topics that can be very confusing. Now, before we actually get started, I want to say this is not supposed to be confusing, but it is, right? So I'm going to try to simplify this discussion as much as I can in order for you to understand the concept of noise margin. Now, I'll read the statement first and then I'll talk about how we can relate to noise margin better. Noise margin is a measure of how much noise it takes to corrupt a worst case output voltage into a value that may not be recognized properly by an input. Right? How much noise does it take to corrupt a worst case output voltage, which may not be recognized properly by the input of the following logic gate? To go further, I will do this. I will, let's say, add a paper here, okay? And I'm going to sketch some logic gates as blocks. So let's say I have a block here, and I have another block here, and I have another block here, right? So let's suppose that my goal is to actually connect logic gate 1 to logic gate 2. Suppose they are cascaded one after the other, right? So the output of logic gate 1 has to be connected as the input to logic gate 2, right? For example, a NOT gate getting connected to an AND gate, right? And something else over here, right? So over here, you can see the output of one logic gate is connected to the input of the following logic gate. So that's what we are talking about here. Now, clearly, if this guy says this is low, this guy has to take it as low. And if this guy says my output is high, this guy has to take it as high, right? That's the perfect world, right? I'm outputting a low, the guy that is following me is taking it as low and not something else. Now, in order for us to get that done in a realistic scenario, what could happen? What could happen is, instead of going around, we may, in some practical situations, go like this. Where in the middle, we are essentially adding noise. Not we are adding, noise may be added due to noise creating factors, digital noise, thermal noise, any noise in the circuit that may be added. That is not on purpose, it is accidental, of course, right? That's undesirable, but it is happening because it's a real circuit. Now, what could happen over here is, this noise might be too much. And if it is too much, it might actually take a low voltage and make it undefined here. And it might take a high voltage and also make it undefined. Right? So we said for CMOS technology, there are range of voltages, right? So for example, any voltage that is between 3.5 and 5, that is high. Any voltage that is between 0 and 1.5, that is low. We established that. Now, when we add some noise to those low and high voltages, we may end up in the invalid region or the undefined region, which is between 1.5 and 3.5 essentially. We don't want that to happen, right? So who is more prone to this noise? Well, of course, the weak 0 and the weak 1 are more prone to this than a strong 0 and a strong 1, because they are far away from that edge. So that is why we talk about the worst case, right? The worst case output voltage, and not just any output voltage. We are talking about the worst case output voltage. Now, noise could corrupt that so that the input doesn't recognize that properly, right? So low is being recognized as undefined, or even worse, as high, right? Now so that's the motivation, right? So we are trying to say, how much can we tolerate? That's the answer. How much can we tolerate? The answer is, find the noise margin. So noise margin is actually a measure in voltage that tells you, okay, 0.5, that's how much noise you can tolerate without a low being recognized improperly, right? And 0.6 is the voltage that is what you can tolerate for a 1 to be recognized incorrectly, right? So that's the noise margin. That's what we are trying to compute. Now, let's go into this. What is this diagram suggesting? Actually, this diagram is everything with respect to noise margin. This tells you everything. On the leftmost, so what is the the vertical axis here, it's the voltage. There are 3 columns. One is for output voltages for logic 0 and logic 1. The rightmost column is the inputs, input voltages for logic 0 and logic 1. And in the middle here, there is an invalid region for the inputs. And of course, over here, this is the invalid region for the outputs. Now, suppose the output of logic gate 1 is logic 0, a 0, right? What would be the worst case scenario? The worst case scenario for me would be here, right? What is that? That's 1.5 volts. If this is 0 volts here, that is maybe 1.5, let's say. Actually, let's make it just 1. This is an example. That's just make it 1, right? 0 and 1. So any voltage that is between 0 and 1 volt as an output voltage for logic gate 1 is logic 0. However, that same voltage is being connected to an input of logic gate 2. And it may recognize any voltage between, say, 1.5 and 0 volts as logic 0. So what would be the noise margin? Noise margin for low level. 0.5, absolutely right. 0.5 is exactly right, because that's the difference, right? I can be here. So for example, if I have a noise of 0.1, I'm okay. It will still be recognized. 0.2, sure. 0.3, sure. 0.4, sure. It will still be recognized as logic 0 as the input to the next gate. But if I go to 0.5, I'm at the edge. And if I go even further, I will actually recognize that as invalid, right? So the logic gate 2, the second logic gate, will see that as invalid. It is not going to recognize that properly, right? So the noise margin is going to be what? 0.5 volts. And what did we have to do for this? We had to just subtract. That's it. We had to just subtract these two values and we are done, right? So it's just a subtraction. That is all. Now, in order to, and the same thing happens at the high level as well, right? So for example, let us just put some values here. Let us say this is, just say, okay, maybe in the green, let's say this voltage is maybe 3.5, and let's say this voltage is, oh, let's make it 4.5. Let's make this 4.5, and let's make this guy over here as 3.5, right? What is the noise margin for the high level? 1 volt, perfect. So I can tolerate about 1 volt. If I go more than 1 volt, it will be in the invalid region, and I will not recognize that as logic 1. Right. So the noise. So what would be the subtraction here? I would need to subtract those two values. Simple, as simple as that. Subtraction. Now, what will help me over here is to have some names for these values. The 4 values that I've highlighted in pink, I want to call them with a certain name so that I can understand them and I can apply them to any problem. So what I'm going to do is I'm going to call this guy, let me call them in black. Okay, so the lowest, the minimum voltage that is at the output being recognized as high, right? That's 4.5. So I'm going to call that V output high minimum. And then of course, this guy will be V output high maximum. that is not going to play a role in my subtraction. O for output, H for high level, minimum for the least value that is recognized as high. Next, what do I name the 1 volt mark? This guy. What do I name that? Think about okay, so answers are all right. O output, low, maximum. Good. And then this guy will be output, low, minimum. Perfect. Now let's go on to the other side and talk about, let me highlight them a little bit, maybe with blue. Let's go on to the other side and talk about these guys. For the input side, what should I name this? Voltage, input, high level, maximum. Voltage, input, high level, minimum. Voltage, input, low level, maximum. Voltage, input, low level, minimum. Yes, yep. So I've got these 4 as well. Now let's compute noise margin for the high level. And I'm going to write the formula all the way at the top. Noise margin for the high level equals what? What should I subtract from what for the high level? I'm going to start writing this. You guys can correct me if I'm wrong. VOH min minus VIH min. VOH min minus VIH min. Perfect. That's for the high level. It doesn't have to be the same for the low level. They can be different. Most cases they are almost the same. Next, for the low level, I will write here noise margin for the low level. Let's see. What should I do here? Low level. V input low maximum minus V output low maximum. VIL max, VOL max. Perfect. That's it. If I know those 4 values, I can find the noise margin for the low level and for the high level. I'm fine. That's your noise margin, right? So I hope that this discussion helped with the concept of noise and what can we tolerate. Now let me ask a related question. Would you want your noise margins to be high, or would you want your noise margins to be low? All right, so there are 2 highs and 1 low. Okay, so here there is a difference between noise and noise margin. Noise we want as less as possible. Noise margin is a measure of tolerance to noise. We want that to be as high as possible, right? So we want our circuits to be tolerant, more tolerant to noise than less tolerant to noise. But if we just talk about noise, we want less noise. So low is the right answer for noise. High is the right answer for noise margin, right? If we have a higher noise margin, then we have a higher tolerance to noise. All right, so let me just write it over here. High noise margin is better. More tolerance to noise. All right. Let us move forward here. I think there is a big lag between when I'm writing and when things appear. Huh. All right. Now let's come to applying this concept of noise margin to actually calculate a noise margin of a NOT gate. Now, this is a CMOS inverter or a NOT gate that is based off of CMOS technology. So essentially you have one NMOS transistor in pull-down network, one PMOS transistor in the pull-up network, and we know how to construct that using transistors. So because this is a NOT gate, as you increase the input voltage, your output voltage goes down, right? So as you increase, so when your input voltage is low, your output voltage is high, indicated by that line over there. And as you increase the input voltage, say beyond 3.5, your output voltage has gone down to 0. So that's your input-output transfer characteristic of a NOT gate. So the first assumption over here is, what is a high voltage? So when you think about the input, any voltage that is more than 3.5 is considered as high. And any voltage that is below 2.5 is considered as low. This is for the input side, of course. Now, let's take a look at the output, right? When the input is 3.5, the transfer characteristic tells me that the output is going to be 0.8. So there are multiple lines because there were multiple experimental trials, right? So don't get confused by that. It is just multiple trials or multiple NOT gates we are showing on one graph. We are interested in only 4 values. You guys remember that, right? We just need 4 values and we do the subtraction appropriately and find the noise margins. Now, when the input is 3.5, the output of the NOT gate is 0.8. And when the input is 2.5, the transfer characteristic tells me that the output for that input is 4. So using the same terminology that I have before, let us call these guys their appropriate names. So what is 4 volt? 4 volt is an output. It is for the high level and it is the minimum. 0.8 is output low level maximum. 2.5 input low level maximum. 3.5 is voltage input high level minimum. Yes. That's all I need, right? Because I already have the formulas to calculate what the high noise margin and the low noise margin are going to be from before. So for high noise margin, using the same concept that we did before, I would just simply subtract 4 minus 3.5. Output high minimum and input high minimum, both the minimums. And then for the other case, low noise margin, I would take the lows. Input low maximum minus output low maximum. And if I calculate that, I find out the noise margin for the high level and the low level. So it turns out that my low level noise margin is much higher than the high noise margin. So my tolerance to noise is much better at the low levels, in this case, right? That's it. That's how you calculate. I'm confused. What makes 3.5 volts input high minimum? Because we are given that. So you would have to be given those two things. Now, from those two things, you can use the graph to get the other two things. And once you have the four things, you can do the subtractions appropriately. Now let's do another example here. This example, you are given the input-output characteristic, and you're also given two things that we need to start with, right? Two things that should be given information. So those two things are, any input voltage below 2 volts is considered low, right? And then any voltage that is above 3 volts is considered high. So those two things are given to us. Where are they? Well, one is probably right here, and one is probably right here. Say this is 2 and this is 3. Let me also highlight some points that may be of interest to me. What is that point? What is the ordered pair there? Well, input is 1, output is 5. What about here? Input is 4, output is 0. Now, obviously, once I have the 2 points, I can find the equation of the line, right? Equation of line. I can find that out using 2 points. One point is right here, and the other point is right there. Now, once I find the equation of the 2 points, I can use the information that is given to us for the 2 volts and the 3 volts input to find the corresponding outputs. So for example, I would need to find that guy, and I would also need to find that guy. Once I have those, using the equation of the line, I can then focus on calculating the noise margin for the low level and the high level. And another related question is, can we do something to increase the noise margin by maybe setting a different threshold voltage for low and high? So right now our threshold is 2 and 3 volts. To increase that noise margin, can we play around with the thresholds? So we'll see that, right? So hopefully now you guys are okay with where we are going with this, right? Equation of the line and so on. So the problem is actually solved over here for you. The output, which is on the y-axis, right? So let's see, y equals mx plus b, right? We have seen this equation all the time. What is our x over here? Our x is the input, V in, and our y is the output, V out. I can find the slope because I know the 2 points from earlier. The 2 points were what? 1, 5, and 4 and 0. I can find the equation. And then the slope, so once you have those and find the equation of the line, it will come out to be this. Using those 2 points, you can write the equation of the I/O characteristic as a linear function. V out equals -5/3, that will be the slope, times V in, plus the y-intercept will be 20 divided by 3. Now, what is going to be the noise margin for the low level and for the high level? Well, for that I need 4 points. I already have 2 of them, 2 and 3, because that was given information. Those were the thresholds for the input, as below 2 is low, above 3 is high. That was the given information. And using the equation of the line, I would find their corresponding outputs. Once I do that, I know the 4 points that I need to do the subtraction. In the same way as we did before, high noise margin will be 10 divided by 3 minus 3. You will get 1/3 here. For no noise margin, you will do 2 minus 5/3. Same equations. And you get 1/3 again. That is when your thresholds are this for the input. Now looking at the math over here, what is in my control? What this is in my control, right? Oh, come on. This is in my control. This is in my control. Can I do something to those two numbers to increase my noise margin? Raise 2 and lower 3. If I want a higher noise margin, I would need to not only change that, but my output will also change. So if it's not, like just that straightforward. When you change that to 4, for example, my output correspondingly will change to 5. And then when I change lower 3, oh, no, it's not in our control. We are just trying to see when do we get the better noise margin. So if you are, say, purchasing logic gates and you want a logic gate that is of higher tolerance, then you would want to look at your the thresholds that are acceptable to that logic gate as input low and input high, right? So we don't program that. It is a consequence of how it is manufactured. So when you change the thresholds to 4 and 1 instead of 3 and 2, your outputs also change. And so now your points are above 4 is high, below 1 is low. It's the same equation as before, but our corresponding outputs have changed to 0 and 5. And because of that, our subtraction has become 1 and 1 for both the high and the low levels instead of 1/3 each. So it has increased, hence better. So what would you do? You would move this guy here and you would move this guy here, right? So increase 3 and lower 2. That's what you would do. And the function about V out and V in will be with the logic gate. Yes. So that the transfer characteristic is also something that is fixed by the person who is manufacturing the gate, right? So once they do the gate and they make the measurements for each input, they plot out the output. That's how you get the transfer characteristic. All we are doing is we are taking a more realistic looking transfer characteristic as shown over here, and then we are trying to make a linear approximation to that so that we can do some calculations, rough calculations, approximate calculations. All right. And hence we made it better, right? Questions about this? How are we doing? Noise margin is a simple subtraction operation. I need 4 points. Given the input-output characteristic and 2 thresholds, I can find the 4 values I need to perform the subtraction for the high level and for the low level. Low noise margin is bad because that means lower tolerance to noise. High noise margin is better because that means higher tolerance to noise. Noise itself, you want as less as possible in your system. Okay. Now let's talk about fan in, fan out. Are there limitations to the number of things we can connect to the input of a logic gate, or the number of things that you can connect to the output of the logic gate? Let's talk about that. Many of you were asking a question in the previous class about, is there a limitation? We are trying to address that. So what is fan in? Let us define that first. Fan in is simply the number of inputs to a logic gate. We will see why we cannot have an infinite number of inputs to a logic gate. As the consequence will be logic 1s and logic 0s will no longer be recognized as logic 1s and logic 0s. So they will be incorrectly distinguished as 1 or a 0, right? So that's the problem. Fan in defined as the number of inputs to a logic gate. So for example, what is the fan in over here? Eight. Oh, come on. How about fan out? Oh, how about here? What is the fan in? So let's see, maximum fan in. Maximum fan in of this circuit. Let me call that logic diagram. So it is for a logic gate. 4, yes. So one guy has 4, one guy has 4, one guy has 2, one guy has 1. The maximum is 4. So the max fan in for that particular logic diagram is 4. But for the one on the right is 8. The left guy and the right guy are actually the same. They are both 8 input NAND gate. One has a maximum fan in of 4 and the other has a maximum fan in of 8. And the left one is better because it has a smaller fan in, because the number of things that we are connecting to the input are actually less. So my claim right now is the left one is better with respect to fan in. Because I'm connecting lesser number of inputs. What's the limit on the number of inputs? So we'll do some calculations to see what that number is. Right now, there is no such limitation. We are just talking about which one is better or worse. A lower fan in is better because the corruption of the voltage levels is not much. A higher fan in could lead to the corruption of the voltage levels. And we will see that, how it gets corrupted. So I would want something that has a lower fan in, like this, right? 4 is better than 8. That's what I'm claiming. But to get something to be better, I have to give up something that is worse, right? So there should be trade-offs. So what is the trade-off for this? So when you think about the two things, they are logically the same. They are both 8 input NAND gates. What is? Can you think of some aspect of circuit design that is better in the right gate? More gates needed. Okay, so more gates lead to what? More gates lead to what? Okay, complexity, time. So the increased propagation delay. So the design trade-off over here, well, sure, yeah, power consumption is there. There are other things, but I wanted to hit the propagation delay because that propagation delay and fan in limitations are direct trade-offs. By voltage corruption, do you mean a change in the noise margin? No. It has nothing to do with noise. It has to do with voltages. Think about it. We'll get there. Like, just hold on to that question. I'll talk more about how that voltage corruption is happening. So fan in and propagation delay, they are trade-offs, design trade-offs. Power consumption, that is also a factor, but it's not a huge factor. Propagation delay can be critical. Next, what about fan out? What is fan out? Well, if fan in is the number of inputs to a logic gate, similarly, fan out is the number of gates, logic gates, connected to the output. What does that mean? Well, something like this. Think about it like this. There is one logic gate here, and the output of that is connected to this guy, connected to this guy, connected to this guy, and so on, right? So if we just have 3, for example, there are some logic gate. Oh, sorry. This is logic gate 1, 2, 3, 4, right? So the output of logic gate 1 is being connected to the input of 2, 3, and 4. So the output over there is driving the inputs of many gates. And in this case, the fan out is 3, the number of gates that are connected to the output of a logic gate. There is a limitation on that as well, because again, the same problem of voltage corruption, and I'll talk about that as well. We talked about we indicated to a relationship between fan in and propagation delay, right? So propagation delay is the lag between when there is a change in the input and the corresponding change in the output. So for example, if you have Z equals X or Y, right? So we are saying X is an input, Y is an input going through an OR gate, and Z is the output. It's an OR functionality. So when X changes, for example, see what happens. These are timing diagrams, right? So what is this? This is saying for some amount of time, for all these guys, the x-axis is time, y-axis is amplitude. So let me just sketch that. This over here you have time. Here you have low, high, low, high, and low, high for X, Y, and Z. These are called timing diagrams because they show how X, Y, and the output Z are changing with respect to time. When are they low? When are they high? And as they are changing, you have a slanted line showing that during that time, it is actually going from low to high. So when there is a change in X, Z doesn't change immediately. Because remember, inside a 2-input NOR gate, OR gate, how many transistors do we have? 1, 2, 3, 4, 5, 6. 6 transistors, right? There are 6 CMOS transistors inside that guy. 4 for NOR, 2 for NOT. So it is going to take some time, even though it is going to be very, very small time in the order of maybe tens of nanoseconds. It is still going to be some time. So as we can see here, we are just trying to exaggerate that difference in time to look at propagation delay. When X changes, Z doesn't change instantly. Z changed after the propagation delay of the OR gate. When Y changed, Z changed after some propagation delay, right? That's propagation delay, propagation delay, propagation delay, propagation delay due to the OR gate. Let's see. So it's like ping, but for trans. Yes, yes. But, pinging, things are going back and forth, right? Over here is just one way, input to the output. Is it due to the gate operations? It's actually due to the transistors that are present inside them, right? So transistors meaning there is a circuitry, right, that represents OR gate. And things are going to take some time to propagate through those transistors and the wires. even though that is going to be very, very small, of the order of few nanoseconds, there is some propagation delay, right? So essentially that, right? So when there's a change in the input, the output doesn't change instantly. There is going to be some time, right? Now, you can think about it like this. When you switch on a light in your room, for example, if you flip a switch, does the light come on exactly at that moment, or there is maybe a couple of nanoseconds delay? Well, of course there is a delay, right? Because there is a circuitry involved between your light switch and the light bulb. That would be the propagation delay through that circuitry. Over here we are talking about logic gates. Are there any times we would want a propagation delay? Oh yes, Tyler, you have asked us such an elegant question. Yes, there are times we would want a propagation delay. And I wanted to keep that a secret until we go to the middle of the semester, but you have already raised that topic. So it's a very interesting question. Yes, there are times when we would there are times when we would want propagation delay, and the reason is memory. If you want to store a bit of information, we would want propagation delay actually helps us store information, store one bit of information. So this will be maybe in the middle of the semester, but that's when we start talking about sequential circuits that have the ability to store information. That's when we would want a propagation delay. But all the other times we don't want propagation delay. All right, let's move on. Now, many of you have asked this question. What is the limitation? What is that voltage corruption? Here is the answer. So let's try to take an example of the fan-in limitation for a NAND gate. So what you have is a NAND gate, and you have two of them actually. This guy is a 2-input NAND gate. And the other guy is a 5-input. 1, 2, 3, 4, 5. 5-input NAND gate. And what I have done is I have represented the transistors as resistors, because for a voltage they are essentially functioning as a load. Now what is going to happen? So let's talk about the 2-input case, right? In the red, when you have 2-input NAND gate, and when both the inputs are high, what is going to happen? Well, if you have both the inputs as high, you are going to have a low R for the pull down network, low R for the pull down network, even for the second transistor. Why is that low resistance? Well, because the NMOS transistors, when both the inputs are high, are going to be essentially short circuit, right? The source and the drain terminals will be connected together. So that's going to be what? Low resistance here. But for the same time, because the inputs are also controlling the gate voltage of the PMOS transistors, those two resistors are going to have a high resistance, because they are going to be essentially open circuit. That's when the connection between the source and the drain terminals is cut out. It's an open circuit. That is represented as high resistance. And if this happens, because this is a NAND gate, when the inputs are high, let me use red here. Low and low, high and high, high and high. What do you expect for the output? You would expect a low for the output, right? Absolutely low for the output. And V out is measuring across two resistors that are connected in series. So the resistance is less, and hence the voltage drop across that will be low enough. And you will be able to get a low V out. That's good. But now try to think about the second situation in blue. You have a 5-input NAND gate right here, which means you have 1, 2, 3, 4, 5 low resistors that are getting added up in series that could lead to a significant enough resistance such that V out becomes high, and you incorrectly go to H here. That you don't want, right? It's a NAND gate. So when the inputs are both high, you want the output to be low. But if you add too many inputs, they're smaller, and this doesn't happen for the other cases when the input is low, right? This happens only when the input is high, but it is one of the combinations. So I have to design to include that in my design, right? You guys see that? What could happen if I have more and more inputs to the logic gate? Resistance adds up. Even though it is a low resistance, when it adds up, it can put V out over the limit. So are the resistors just over? No. So you see this. If you have multiple resistors, right, they are all in series. 0.1, 0.1, 0.1, 0.1. But because they are all in series, they add up to be 0.4 ohms, right? Voltage drop would be high. Absolutely. Because what is it? This is essentially a voltage divider, right? 5 volts getting split between high resistance and all of that. And we are using V out. That's a simple voltage divider. Voltage drop would be high at the output. And that would essentially, no, they don't burn out. It's just their accumulation. The accumulation of all those low resistance can all right. V in plus minus, V out plus minus, 1K, 1K. This is 5 volts. What is V out? Yes, it is essentially a voltage divider. Yes, 2.5. Yes. Now what I'm going to do is this. I'm going to make this 10K. What happened? Yes, from 2.5 it jumped to over 4 point something, right? 4.54, yes. You see that as you're increasing the voltage, V out is increasing. Yes. And this could be 1K, 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 1K. So they are essentially, yeah, this is using V equals IR, yes. So it's based on Ohm's law, but application of Ohm's law to a circuit with resistors in series, you can derive the voltage divider equation. That's what we are applying here. All right, and we don't need to know it. No. Yeah, we don't need to know I. It's all right. Let's I is V divided by R, right? So 5 divided by 11K for this circuit. like we wouldn't need to find that out for this application. The point of this is, as you are putting more and more resistors in series, each of them is small, but when you put them in series, they add up and voltage across them increases, and that puts it over the limit. Now V out could be high, and that may not be recognized as low that we want for the, yes. V out is R1 divided by R1 plus R2 times V in. That is for voltage being across R1. Over here, earlier we were measuring about R2. It doesn't matter, but I think you guys get the idea. It's an application of voltage divider. Now let's talk about fan out limitation for a NAND gate. Yes, as you increase resistance, the voltage drop across that resistor increases. All right, so let's see, fan out limitation. So we are talking about, all right, there could be a limitation on the number of inputs you connect. Is there a limitation of number of outputs you connect? So again, over here you have two situations. One in which you are connecting nothing to the output, right? So there's nothing connected here to the output of a NAND gate. And the other situation, you have 5 things connected, 5 gates essentially. 5 logic gates connected to the output. So let's take a look at what happens when you connect logic gates at the output. Well, 2 input NAND, when both the inputs are low, V out will be high enough. You see this? When both the inputs are low, the NMOS transistors are going to be close to an open circuit, which means I can represent that as a high resistance. And when high resistance here, V out will be high enough, which is fine, which is good, right? This is absolutely good. That's what we want. When both, not blue, that's for red. Low output should be high. That's what you can get with this. But consider the case when you connect 5 logic gates to the output of that 2 input NAND gate. You are connecting 5 things, 1, 2, 3, and so on, 4 and 5. When you connect 5 things to the output of the NAND gate, all of those guys are going to be parallel with each other because they are sharing the points. One is there, one is the ground, right? So they are effectively going to work as 5 parallel resistors. Now, when you have 5 parallel resistors, what is going to happen to their overall resistance? The resistance gets lower. You got it. It goes down. And when it goes down, what is going to happen to the voltage? When the resistance goes down, when the resistance is going to go down, voltage proportionally is going to go down, right? Again, the same voltage divider, right? V out will go down. Now, V out goes down. The problem could be V out is too low. We don't want that, right? We wanted, for that particular case, when both the inputs were low, we wanted the output to be high. In this case, we got, because of connecting too many things at the output, we got a low output. So that's essentially your fan out limitation. Maybe if you had just one resistor or 2 resistors or 2 logic gates connected at the output, it may not have been low enough. It may not have been too low. But because you connected 5, it became too low. So voltage divider, logic transistors being represented as essentially resistors of low and high impedance. That's what we are. But would a buffer fix this? You are right on target. So a buffer will fix this, and it is actually meant for that purpose. A buffer is exactly meant for that purpose, to make a weak 0 into a strong 0 and a weak 1 into a strong 1. That's exactly what the purpose is. So in the logic diagrams that we are going to see maybe in the coming weeks, you will see a buffer in scenarios where there are too many things connected to the output of a logic gate. And now you know the reason why. Is that the only what a buffer is used for? No, a buffer can be used for other things as well. It can be used for disconnecting things. So for example, a buffer can be in one of the three states: low, high, or high impedance, right? So there are other applications of a buffer, but in the context of fan in and fan out, a buffer is the solution. Another solution is this: give up on propagation delay. Come on, let's go. So that's another solution. If the fan in is too high, you can always break the circuit down to do the same thing, but you'll have to give up on propagation delay. I hope you guys see that these two circuits are equivalent, right? So the way to quickly check this is this: the NOT gate essentially cancels out with that bubble. So these two cancel out. What you are left with is NAND OR and NAND. That's essentially what an 8-input NAND is doing for you. All right, I'm going to stop recording here. I believe that was the last slide for today. Yes. All right, I'll stop recording here.